Look upon America as it is today, changing and evolving, facing new challenges. A nation building to the future upon solid foundations of the past. Over the vast expanse of America, men have dreamed and built prodigiously. But to give substance to the dreams, there had to be a material equal to the task. That material was and is steel. Today, out of every 2,000 pounds of all metal used in America, over 1,800 pounds are iron and steel. But why steel above all other metals? What is it? Where does it come from? How is it made? The answers are to be found in many places. But first we must consider iron, for steel is iron. So let us go back 1 billion years or so and begin that part of the fascinating story. After ages of wild and tumultuous geological evolution, the Earth began to cool. In the primeval basins, the oceans appeared, and for centuries, the rains continued to fall upon the smoking, blasted surface. As the waters flooded over the Earth, they loosened and dissolved the soil, and much of it was carried along by streams and rivers, eventually finding its way into the lakes and oceans. On the bottoms, heat and pressure eventually transformed sediments into layers of rock. Continuing upheavals in the cooling crust often caused them to be folded and cracked and thrust up to be exposed to the eroding effects of the elements. Sometimes a mass of molten material would boil up from below. Often rich in iron from the crucible of the Earth's interior, the molten material usually dissolved the host rock and replaced it, solidifying into a mixture in which the concentration of iron is quite high. This we call iron ore. There are billions of tons of iron ore deposited around the world, but of course it must be converted to other forms before we can use it. To demonstrate simply the basic steps in the next part of our story, let us call up from an earlier time an iron master, one who learned from the ground up. Obviously, the ore had to be removed from the ground, so whether it was found right on the surface or had to be mined, the first step was...
digging!
Yes, digging. The ore was often found in more or less inconvenient places, so the next thing to be done was...
hauling!
That's right, hauling. The next step, a most important one, was...
smelting!
That's correct. Smelting, getting the iron out of the ore. For this, a large furnace, often made of stone, was necessary. There had to be huge bellows to blast air through and make the fire hotter. And there also had to be...
charcoal and limestone!
Correct. Charcoal and limestone. The charcoal was fuel for the fire. And while our friend here didn't know it, it also furnished carbon for chemical reactions that helped free the iron in the ore. The limestone was put in because it soaked up impurities, forming a slag which could be discarded. The smelting process was begun by dumping layers of ore, limestone, and charcoal into the furnace. Into the furnace. Finally, the blast furnace was ready to be tapped, and the iron, which was now melted, ran out the bottom into a trench. Since this rather resembled a family of little pigs, the iron came to be called pig iron. Now the iron had to be turned into something useful, and casting the molten metal was one of the ways this was done. When it cooled, this cast iron was very hard, and many useful items could be made from it. However, it was not practical for some things because it was quite brittle. In another method of converting it into useful form, bars of the iron could be reheated and refined in forges and beaten into various objects. Called wrought iron, this kind was strong and tough and could be made into other useful items. However, for some things, it was too soft. Obviously, there was a difference in the two kinds of iron. Our friend didn't know exactly why this was, but he learned that he could make even another kind by putting the soft iron in clay pots, adding a certain amount of charcoal or other carbon, and making his fire hot enough to melt the iron. Getting enough heat was difficult, but this was the secret of the process. The iron he obtained this way was very special, for it combined the best qualities of the others. It was even given a special name, steel. It could be shaped by hand. It was supple and flexible and would not shatter. Yet it was hard and tough and would stand up under difficult conditions. But because it could be made only in small quantities, steel was rare and precious, worth its weight in gold. Even as late as the founding of the colonies in America, steel was very scarce. But iron was so essential that one of the first industries was an iron works built on the Saugus River in Massachusetts in 1644. The original house of the ironmaster still stands near the Saugus, and the ironworks itself has been so faithfully restored that we can actually see how iron was made in the early days of our country. The iron ore and charcoal and limestone were dumped by hand into the top of the blast furnace. The waters of the Saugus were put to work turning giant wheels that in turn operated such things as the big bellows that forced air through the blast furnace. The furnace was built of native stone and could make about 3 tons of iron in a day. Once or twice a day, the tap hole was opened and the molten iron flowed out to be cast in pigs or other items. There were forges where the bars of pig iron were heated and refined, and a 500-pound trip hammer for pounding them into high-quality wrought iron, and a rolling and slitting mill where the bars were guided through by hand to make strips and rods. This project, big for its time, was built with the savings of many individuals, in much the same way that large companies are created today. During the Revolutionary War, iron played an important role. There was some steel for swords and small weapons, of course, but it was iron for cannon and cannonballs and pots and kettles upon which the Continental Army depended. There was even an iron chain with links weighing 100 pounds apiece, stretched across the Hudson to keep the British from coming upstream by ship. Also, George Washington was the son of an ironmaster, and Valley Forge itself was originally an iron works. After the war, the number and size of blast furnaces and forges grew rapidly, and the iron that flowed from them became more and more essential to the nation. Again, it was investment by individual stockholders that made this expansion possible. Now, railroads appeared on the land, and steamboats on the rivers, and factories and machinery in the cities. A small amount of steel was available for special uses, such things as the blades of the history-making McCormick Reaper. But even as late as the Civil War, iron was the only metal in abundant supply. However, as the guns of war fell silent, this was about to be changed. In 1864, 2.5 tons of steel were made in minutes in a device called the Bessemer converter, and the age of steel had arrived. Now at last, steel could be made in quantity and at low cost. To raise money for further growth, iron and steel companies issued new shares, and in the stock exchanges of the day, they were eagerly purchased by investors large and small. On every side, the spirit of freedom and individual enterprise acted as a catalyst, and the stage was set for America to take her place on the world scene. Steel was a major factor in the unparalleled growth and development of America. Steel, because of its strength and versatility and low cost. But ask now, what of steel and America today? Iron and steel are presently produced by 275 companies in America, and the industry's capacity has increased tenfold in half a century. More than 1/2 million people have jobs in steel, and ownership of the companies is shared by several times that number. New construction often involves hundreds of millions of dollars, but continued growth in steel making is essential to the nation. In the industry today, marvels of engineering have become almost commonplace. But even so, we must still first obtain the raw materials from the earth. Remember, our old friend had to do this too, but he had to find ore that he could dig and haul away 100 pounds or so at a time. Now it's tons at a time. And while some of it is still used as it comes from the mines, the greater part is low-grade ores, once thought useless. The most important of these is called taconite.
What's that?
That's a machine for drilling taconite. Jets of flame pierce holes in the rock. The holes are filled with high explosives, and then giant-sized shovels scoop up the rock, and it's hauled away by the trainload. The cars are dumped 2 at a time by specially designed equipment. In huge plants, the rock is pulverized and washed, and richer iron ore is separated out magnetically. Now the iron-rich powder is fed into large drums to be made into pellets. Moving belts next take the pellets to a furnace where they are hardened by baking. Finally, the pellets are loaded on ships that transport them to the places where steel is made. The ships are of a special kind, the larger ones designed to carry over 50,000 tons of ore. In addition to the iron ore mined in the United States, millions of tons are brought in from Canada and other countries. Now great quantities of coal must be clawed out of the earth. Ton upon ton of limestone must be quarried, and alloying elements brought in from all over the world. At the mills, the coal is baked into coke. The raw materials are dumped into huge piles, and only now are we ready for the next step. Going back to our old iron master, his next step was...
Smelting, of course.
Yes, smelting. Although blast furnaces have changed somewhat, as might be expected.
But I'm a doggone.
Giants such as this, amazingly engineered, can turn out 8,000 tons of pig iron per day. The raw materials are still hauled up and dumped in the top, but now it's done by the carload. And today's iron makers have sensitive instruments and electronic computers to tell them what's happening inside. After the furnace is tapped, the molten iron flows as before, flaming and hissing in the runners. The scenes are weird and spectacular, blazing with heat and fiery glare. The work may look dangerous and even frightening, but because of training and proper safeguards, the records show that this is one of the safest of all industries. Now the molten iron must be taken away from the blast furnaces for the next step, transformation into steel. In the open hearth method, tons of scrap steel are first charged into long banks of furnaces, then the molten metal is added on top of that. Impurities are boiled away by flame at nearly 3,000 degrees. In another method of making steel, furnaces that depend upon electricity are used. Enormous electrodes flashing in blinding arcs generate the heat to melt scrap iron and steel. Stainless and other special steels are made in this type of furnace. However, most steel is made by a third method called the basic oxygen process. Scrap steel is charged into the furnace with speed and efficiency. And molten iron is added quickly, for every minute counts. Here's the heart of the process, a pipe through which pure oxygen is blasted at supersonic speed. Combining with the materials in the furnace, the oxygen generates its own heat to purify the iron into steel. The basic oxygen process is a very rapid and precise way of making steel, and every batch is checked at exact intervals. Measuring devices feeding information directly into computers permit almost instantaneous analysis and assurance that the composition of every heat of steel is exactly correct. In a variation of this process, oxygen is blown in from the bottom instead of the top, and the furnace is totally enclosed. In all steelmaking methods, there are waste products, which, if uncontrolled, would escape into the atmosphere, as in this brief demonstration. However, with present control systems in operation, most pollutants are removed and only clean water vapor is finally released. Such environmental quality controls are common among steel companies, which have spent as much as any other industry in this area. For example, this water treatment system cost $18 million, but it can clean 140 million gallons of water per day. This air pollution control installation reduces possible emissions by more than 99%. And while such equipment adds enormously to the operating costs of steel companies, realistic environmental standards are being met. At the same time, production must be increased, for America has an even greater need than ever for this vital material, steel. But molten steel, however made, is an intermediate step, and it cannot remain long in the brimming ladles. In the traditional method, the ladles are now swung into place over long files of empty molds, and the molten metal is poured out in an operation called teaming. Later, the molds are stripped off, and at last there are ingots of steel in solid form. Now let us return for a moment to our old friend. He made steel in a different way, but the end result was still an ingot of steel. Of course, a plain lump of steel is of no use, so as may be remembered, he had to hammer it into shape. Ingots today are usually 15 or 20 tons, but they have to be shaped too. However, again, the methods are rather different. With fingertip control, highly skilled steel workers push the ingots through rollers that act like giant ringers, squeezing the steel repeatedly into longer, thinner pieces known as slabs. The newest method of shaping steel is called continuous casting. Ladles of molten steel are emptied into a container called a tundish. The tundish must be kept in constant movement as the hot metal drains continuously out the bottom into a mold. The mold is water cooled, and the steel begins to solidify as it descends. Continuing to move, the metal is cooled further by still more water sprays, finally emerging as a thick ribbon of steel up to 7 feet wide. As the glowing ribbon moves along, a huge torch moves with it, cutting it into any desired length. In this way, steel slabs are produced directly from the molten metal. Slabs are made in many shapes and sizes, and they go through many different kinds of finishing. They are rolled and re-rolled, becoming thinner and thinner. They may be taken off as plates of steel to be made into railroad cars or storage tanks or the like. Or at other times, the steel is rolled into a very long, thin sheet. Steel workers use electronic computers to keep track of every piece of steel and control the entire operation. Now, as the strip becomes longer and thinner, it must go faster. It hurtles out of the last mill at 40 miles per hour. It plunges into a cooling spray and finally is rolled up automatically into a huge coil. When cold, such steel is sometimes put on other mills and rolled again, giving it a smoother and harder finish for auto bodies and appliances of many kinds. And some of the steel is given even further treatment. It is coated with molten zinc to make it into corrosion-resistant galvanized steel. Or it is cleaned in acid and plated with tin to make better, thinner, and more economical tin plate for cans to protect our foods and beverages. Some steel is rolled into pipe that carries oil and natural gas thousands of miles across the country. For special purposes, such as the drilling of oil wells, solid bars of steel are made into seamless pipe. In other operations, steel is rolled into the structural pieces we see in bridges and buildings. Some steel is formed into bars, or it is rolled into rods and stacked in glowing coils. Later, it may be drawn out into thousands of feet of wire for fences, nails, springs, and bridge cables. But making steel still demands control of tremendous force. In a specialized phase called forging, ingots of 100 tons are handled with ease. A gargantuan press literally squeezes the ingot into shape with as much as 15 million pounds of force. Smaller pieces of steel are pounded by great mechanical hammers to impart added strength to the metal. Thus, we have seen that many of the steps used by the old iron masters still have counterparts today. But there is a great and fundamental difference. Our old friend gained his knowledge by trial and error. He was remarkably successful most of the time. Today, because of costs and demands for quality, a more scientific approach must be taken, and modern steel company research laboratories are playing a vital part. In these laboratories, research is conducted in many directions, both theoretical and practical. On the theoretical side, many sciences are brought together to probe into the very nature of iron and steel. The most advanced tools available are used, such as microscopes which use streams of electrons instead of light. Magnification of over 200,000 times reveals the intricate structure of steel. This kind of research is steadily increasing our knowledge of the properties of the iron atom, and we are learning how to use more and more of its great potential strength. Practical research is bringing new and better ways of using raw materials. Here, for example, is laboratory equipment for a process called direct reduction, in which iron oxide pellets are made into over 90% pure iron by chemical reaction. Operating plants using this process have been designed, and they will have definite economic and environmental advantages in areas that have abundant natural gas. Of course, there is a constant search for ways to make more steel and better steel at the lowest possible cost. Experiments in automatic and computerized control also seek to improve quality and eliminate energy waste. From such studies have come production methods like this, in which ladles of steel are sealed in vacuum chambers and stirred magnetically. Bubbles of trapped gases that would weaken the steel are drawn off. And for very special steels, ingots hooked up to large electrical transformers are also sealed in vacuum chambers and remelted like candles. This gives even purer, super-strength steels, steel so strong that a pencil-thin bar can lift the weight of a railroad car. In the laboratories, research has provided many improved products. For example, this can, which is now being produced, is made of very thin steel, and it is seamless. This makes it both lighter and more reliable. As another example, long coils of sheet steel are now custom painted on production lines before delivery. Available in thousands of different colors and textures, this pre-coating eliminates a costly step in fabricating many products. On the other hand, steels that never need painting because they form their own protective coating when exposed to weather are revolutionizing bridge construction, especially in locations where maintenance is difficult and costly. Other new products go all the way from high-strength forgings that can take the landing shock of a 180-ton aircraft to steel lumber, with which residential construction is easier and faster, as well as stronger and safer. Also, there is increasing use of designs in structural steel, which make possible huge domed stadiums. Several hundred feet across, they can be built without a single supporting column inside to block the view. The continuing search for new ways to use steel is increasingly important. For as America begins its third century as a nation, we are entering a new and different era, a time of change and challenge on a global scale, a time also when available sources of raw materials and energy must be balanced against an awareness and concern for the needs of the total environment. For the future, America must work and build in new directions to maintain and improve the quality of our lives. It is vital that America be strong and forward-looking while remaining true to its heritage and tradition. The principles upon which America was founded remain, solid as the granite of her magnificent mountains. But whatever the changes and whatever the challenges, steel will remain the material equal to the task.